the idea was that we want to deeply understand every one of these identities. These are the famous ones. And we talked about the first ones last time, so let me do a little repeat and review. They say if a teacher repeats and reviews something, students are more likely to get it. So let's do it. So this whole theme is about identities, and we're sticking to nothing but the famous ones for now. We'll do some of the non-famous ones maybe at one point or another, but let's take it from the top. What is an identity? An identity is a formula that's true for all possible values of the variables, with the exceptions of those values which may make it either side undefined. The short way of saying that is just a formula that's true for all values of the variables, with a little star on that. Second characterization is an exchange rate, where you say, hey, if I bring you a tangent x, what can I exchange that for? Well, you say, oh, I'll give you a sine x over a cosine x for that tangent of yours, and so on and so forth. If I bring you a sine of x, can you give me a cosine, please? And you say, yeah, I give you a cosine of the complementary angle 90 degrees minus x. No problem. If I bring you a secant x, what can I exchange that for? Well, I'll give you a cosecant of the complementary angle. There are exchange rates. So every time if you want to exchange the tangents for sines and cosines or vice versa, the identities tell you exactly how to do it, because they hold true for all possible values of x, except the values that make no sense. I'm going to stop saying that. I'm just going to say for all values of x, and you'll know what I mean, right? Alright, that's where we left off last time. Had a crucial discussion here about different ways of proving that an identity is true. We had this technique: work on each side separately. You abandon the equality, work on each side step by step, so you can determine whether they're really equal or not. Tweak a known identity. In this case, you don't have to abandon an equality. You just start off with something that you know is equal, and you make small little tweaks, little tiny little tweaks. These could be substitutions, or you could be rearrangements of the equation. Could be any of major things like that. Any of infinite many things like that. Third option, we look at the graphs. You graph this one, you graph this one, and then if the graphs can conclusively convince you that they are the same, then you've got a reasonable argument, a proof of the identity. And the fourth one, we'll start with something amazingly brilliant and creative. My favorite. We'll get to that one. We'll save it for last. Alright, and besides that, we got to start our famous identity sheet. Talked about the first four up here. There's nothing to prove there. They're true by definition. We proved these by working on each side. And then we went on to prove these by several ways. One way to prove it was that we stood at different corners of the triangle. Another way to prove it was, that would be a little bit of something creative. Not that much brilliant or creative, but just a little tiny bit. Whoa. Fire hazard. Don't you love it when you beat your alarm clock? I set that at 5 o'clock in the morning. My friends, if you can hear my voice, we're on it already. Alright, anyways, where was I? So we... you guys should turn your cell phones off. So every one of these, you should have a little check mark. We agree that the way we're going to handle this is you go through every one of these, and once you own it, you put a little check mark on it. Okay? And so far, you should have check marks on every one of these, on the top paragraph and on the second paragraph. What's on the menu for today? Today we handle the even-odd identities. Sound good? Are you part of the resistance? Let's do it. So let me tell you a little story about the even-odd. What does that even mean? Well, here's what it means. So if you take a function, say f of x, where f takes on real values and it gives you real values, this means that domain is reals, codomain is reals, or the range is reals. Suppose you have f of x equals x squared. This is sort of a famous one. I'm sure you've seen it before. And you say to yourself, hey, what's f of 3? And you say, oh, that would be 3 times 3, which would be equal to 9. And then you compare that with, say, the negative. What would f of negative 3 be? Say, well, that would be negative 3 times negative 3, which would be positive 9. And you say to yourself, whoa, f of 3 is exactly the same as f of negative 3. F of 3 is equal to f of negative 3. You say, whoa, that was kind of interesting. Maybe, what if it was a different number? Would f of 5 be equal to f of negative 5? And the answer would be yes. They're both the same. This function really doesn't care whether the input is positive or negative. It does the same thing. It discriminates not against positive or negatives. It sends them all to whatever the square is, to the same square, that is. When this happens, if f of x can always be exchanged for f of negative x for all possible values of x in the domain, then we call this if f of x is equal to f of negative x for all x's in the domain, then we call this even. Okay, so at first you might say, well, there doesn't seem to be a correlation between the name even and really it should be called functions that don't care whether the input is positive or negative. That would be a more descriptive name. But instead of calling them functions that don't care whether the input is positive or negative, they were called functions that are even. Okay, and it seemed that at first that might seem kind of strange, but take a look at some. Maybe this will help you try to make sense. Sometimes a name makes no sense with the actual object, but in this case it might make a little sense. Suppose we have a similar function, f of x, with from the reals to the reals, but this one was x to the fourth minus 5x squared. You see this one, if I have f of negative x, that would be negative x to the fourth minus 5 times negative x squared, right? And what would this be? Negative x times negative x 4 times. That would be x to the fourth minus 5 negative x times negative x. That would give you x squared. And so this would also be equal to f of x. So in this case, f of negative x can always be exchanged for f of x as well. Another even function. And then you start to look at the powers here. This one is a polynomial with terms of degree 4, degree 2. In fact, every time you've got a polynomial with just a sequence of terms like this, x to the 8th plus 7, x to the 16th plus 3, x to the 4th. This will, of course, will be an even function because it won't care whether the angle is positive or negative. It will be the same as g of negative x. So then you start to make sense of it. Oh, okay, even has something to do with the makeup of the polynomial. If the polynomial is made up of a sequence of terms, each of degree 2 or any other even 2 or 4 or something like that, then it's called even. So long as all of these are even, we'll be in good shape, roughly speaking. Can't have any constants there. That might throw things off sometimes. In fact, in this case, it wouldn't. But so long as these are powers of even powers, we'll be okay. And so that's sort of the idea between calling them even though they're not really restricted to just polynomials. For us, here's the first even function, cosine. The very first, actually the second on the famous sheet, says that cosine is even. It says that every single time, forever and ever, every angle, no matter what it is, if you have cosine of the negative angle, you can always come to the exchange house, and you've got your cosine of a negative angle, and you know what? You can always exchange it for cosine of the positive angle. Okay, that's what one of the most famous identities says. On the even odd paragraph, cosine of negative x is the same thing as cosine x. Okay, super famous. It says that you can always exchange cosine of positive x for cosine of negative x, or said differently, that it doesn't make a difference for cosine. Cosine doesn't care if the angle is positive or negative. It'll do exactly the same thing to it. Has the same value on the positive or negative angles. And so, by the way, another way to characterize that is if you, here's a second way of characterizing that. if you were to draw the graph, well, actually, let's do it here. Okay, so that's the initial discussion on even functions, and such discussion would not be complete if we don't talk about odd functions. And an odd function is defined to be a function where f of negative x is equal to negative f of x for every x in its domain, meaning that these ones do care a little bit about the angle. In fact, roughly speaking, what it says is that you could take this negative that's inside the input value and you can factor it. It comes right through the function to the outside and it gets put right there. You can factor out the negative. Okay? That's what that means. That's what it means to be odd. And maybe a couple examples are of course, in order now. Here's an example of an odd function. F of x, f going from the reals to the reals, defined by f of x is equal to x to the third. Now, why should that be odd? Well, let's see. Well, that f of x is equal to x to the third. What about f of negative x? That would be negative x to the third power, and that would be negative x times negative x times negative x, which would be negative x to the third, and that would be negative x to the third is f of x. Whoa. That would be negative f of x. And so these sequence of steps shows that this is equal to that, that's equal to that, that's equal to that. Shows that you can factor out this negative. As I promised, this negative can come out, there that goes that thing, can come out through the function. When that happens, we call the functions odd. And it's not an accident that this is an odd exponent. For example, if you had some other function such as f of x, which is equal to 5x to the third plus 6x to the 7th minus 10x to the 11th, this is in fact an odd function. Because every one of these pieces is odd. That's not why. It's because if you check it, f of x, negative x will become negative f of x. And the reason that happens is because if each one of these is odd, when you put in a negative, it'll become a negative one that you can factor out of all of them. In fact, let's do it. Talk is cheap. I'm not afraid. F of negative x, let's check it. That would be 5 times negative x to the third plus 6 times negative x to the 7th minus 10 times negative x to the 11th. And that would be, out of the first one, I could factor out a negative. Now this would become negative x times negative x times negative x. That would be negative 5x to the third. Out of the next one, that would become negative 6x to the 7th. Out of the next one, that would become positive 10x to the 11th. And I could factor out a negative out of the whole thing here. And that gives me 5x to the third plus 6x to the 7th. This is a plus, so if I factor out a negative, that becomes a minus 10x to the 11th. And this is in fact the original f of x from up here. So this becomes negative f of x. And this proves that this particular function is an odd function. And it's not an accident that each of its little pieces, each of its terms is odd, of odd degree. Coefficient, we don't care about the coefficient. The degree is the thing that will determine whether when you put a positive or negative x, it becomes positive or it stays negative. Okay, nice. So the characterization, even, every f of x can be exchanged for f of negative x. Odd, every f of negative x can be exchanged for a negative f of x. That's the characterization. And also, if they happen to be polynomials, it's kind of easy to tell whether this is going to work out or not, depending on whether all of the exponents are even or all of them are odd. By the way, not every function is even or odd. If I have f of x, which is equal to x squared plus x plus 5, this one, if you check it, it's not odd and it's not even. So not all functions are either even or odd. That part is kind of misleading. In some sense, maybe, for some. Alright, so don't let that confuse you. Now, what exactly does this mean for our class? For our class, we have a bunch of functions that are not exactly polynomials per se, at least not in the usual sense. These are trig functions, and the discussion ahead is to figure out exactly which of these are odd and which are even. Some of these you can factor out the negative, such as sine, and some of them don't care whether the angle is positive or negative, such as cosine. So some of these are odd and some of them are even. It's a really, really important discussion. This is a paragraph that we got to master today. Let's do it. Okay, so here's the first one. Cosine is an even function. Cosine of x for any angle x is the same thing as cosine of the negative x. And what we want to do is prove it. Now, every time you want to prove an identity, you always got at least 4 different ways that you can start off. What are the 4 different ways that you can start off? These are the 4 different ideas that you could begin with. Work on each side, tweak into an identity, look at the graphs, or start with something amazingly brilliant and creative. So, if you had to prove this one, you might try, I don't know, let's try abandoning the equality, and let's try to work on each side separately. So you make an imaginary side. Well, let's try the graphing method on these. So this one is pretty easy to graph. The graph is the standard one that we've graphed millions of times. It goes something like this, and the graph stays in there something like that, right? And it goes from 0 to 360, from -1 to 1. Now, how's that compared? This is if you wanted to think about it, this is y is equal to cosine of x. Now, to graph y is equal to cosine of negative x, you look at this equation, you look at that. The only difference is, of course, the negative x. So the positive x's become negative x's. If there were any negatives, they become positives, which they are, but we don't hardly ever draw them. So the graph would look like, let me just see, it would be flipped over here. The x's become positive x's, so this is 0 times, sorry, the x's get multiplied by -1, so this becomes, the new bounding limits on them become -360 and 0. Nothing's happening on the y. There's a flip, so now it goes like that. Well, not like that. Just like that. Then you wonder, are these two the graphs convincingly equivalent? And at first you may have questions because this one's on the right side and that one's on the left side, but then you remember, hey, these are periodic functions. They really do go on forever. And if you were to draw them, if you were to continue just a little piece of the forever part, you see that they really do look exactly the same. Well, but you know, you have to forgive my drawing, but they are the same graph, and so this shows that they're equal. And so that establishes that one, and it does a couple of things for us. One, it allows you to, one way to see why this is the case. Flipping the cosine graph leaves the same graph, so these are the same function, and you put a little check mark and say, hey, I understand that one. Done. And then it does another thing for us. This sort of gives you another characterization of even functions. If you notice let me talk more about what happened here, exactly what went down. If you were to draw the cosine graph, that's the part we usually draw. But if you were to draw a couple periods, you see that positive x's, if you were to flip this, positive x's become negative x's, negative x's become positive x's. If you were to flip it, it looks exactly identical as what we started off with. Positive part of the first and fourth quadrant are exactly the same as flipping them over on these two quadrants, second and third quadrant. That is a general characterization, at least for real functions, for even functions. Every time you've got this even function, this part of the graph, the one with positive x's, will be exactly the same as what you get when you flip it over on the negative side, and taking this one and flipping it over will leave the graph seemingly unchanged. Okay, so, think about that. This one was y is equal to cosine x. Another example that we did was this one, y is equal to x squared. If you take this one and you move it over there, it's exactly the same. Flipping it over this way leaves it unchanged. If flipping it this way leaves it unchanged, that's another nice characterization of even functions, at least for real functions. Okay, that's that one. And then I'll let you think about some of the other ones. Maybe I'll do one more from this paragraph. This one should have a little check mark. Let's try the sine. Cosine is the most famous even function in our trig class, and sine is the most famous odd function in our trig class. Sine of negative x. What happens with this is you always on sine function take this negative and pull it right through the sine function to give you negative sine x. Okay, and we talked about this. Whenever you can do that in a function, this is called an odd function. And so one way to prove this is, of course, again, we always have these 4 techniques. Work on each side, tweaking on it, and look at the graph, start with something to make something creative. We'll take a look at the graphs, and that should be pretty straightforward. Let's see, if you wanted to graph y equals negative sine x, well, a negative next to a sine doesn't really mean anything. But if you multiply both sides by a negative, now it means something. Replacing a y with a negative y, that's a flip this way. So the graph would look like, let's see if we can do it. Let me see. I'll draw the original graph. The original sine graph looks like this. But we want a flipped version of that. We want one where the positive y's become negative y's, and the negative y's become positive y's. So that will look like this. Right? And on the other side, we've got y is equal to sine of negative x. So we draw it. Okay, the original sine graph, without that negative on there, the original one would look like this. But this one has, instead of an x, a negative x. So positive x's will become negative x's. It'll be a flip over the y. And so the graph would look like, so remember, the original sine graph goes over here. If you flip it over there, if you flip it this way, the flipped version of it will become something like this. Okay? And so then the question is, are these convincingly equivalent graphs? And of course, at first you might have your doubts, but you really need to continue these graphs to see if they're the same or not. Once you continue them, then you see that they are convincingly the same, because this one starts off here at the bottom, at the origin. It goes down first and then back up. Same as this one, goes back down and up. I know the drawing is not exactly perfect, but let's just let that slide. And then in that way we establish that these are in fact the same. Sometimes the graphs are not that convincing, but in this case there's absolutely no doubt they're the same graph. And that would be by looking at the graphs we can establish identities. And so that establishes sine as an odd function. And not only that, but that gives you another characterization of odd functions. For odd functions, okay, for odd functions, if you flip this way, you get the same, if you take all the positive x's and all the negative x's and flip them, the picture looks maybe not the same as the original one. That would be an even function. But the picture would look the same as taking the positive ones and the negative ones and flipping it this way. That's the characterization of an even function. Okay? To flip this way is the same thing as flipping this way. Or said differently, to flip this way and then this way leaves you back the original graph. I'll say it again. To flip this way and then this way leaves you back something that's equivalent to the original graph. And that's another characterization of odd functions. For example, I'll give you another example that's famous. Y is equal to x to the third. If you flip it, let's say you flip it this way. If you flip it this way, this would become this way, this way. But then if you flip it this way, it becomes exactly the same as what you started off with. So if you flip it this way, then this way, you get exactly the same. I told you. Didn't I tell you? Super famous characterization of odd functions, at least for real odd functions. Okay, so that's even odd. That puts a little check mark on this one right here. And forever you know that on a sine function, you can always pull out that negative if there's a negative there. Or put it back in if there's a negative is on the coefficient, if negative is out here. Very special. Cosine is even, sine is odd. And some of the other ones will follow the same secant. Of course, the inversion of the cosine. So if this one was even, that one will be even. All the other ones are odd. Okay. I think we should let you have a turn at it.